Right. This lecture is on a statistic, or really two statistics that are called chi-square tests. And I think at this point in the course, it's useful to review some of the statistical tests that we've already covered. Um, and so in this table, what you'll see is in the leftmost column, um, predictor or an independent variable, and whether that is measured using continuous measurement, that is, the values of that variable can take on any value. It's a continuous. You can think of it as a continuous number line. Alternatively, we can have dichotomous, which just means two categories can take on two levels of a variable that are categories. And then here we've got other categorical variables. And then so far, all of our outcome measures or our dependent variables have been continuous. So that when we want to analyze a predictor that is continuous and an outcome that is continuous, we're going to use a Pearson correlation coefficient, or we can do a simple bivariate regression. If we have an outcome variable that is a continuous variable and multiple predictors, we'll do a multiple regression. We will do t-tests. Now recall that we had um, three different types of t-tests. We had a one sample t-test. We've got a paired sample t-test. We have an independent samples t-test. But for our paired samples and our independent samples, when we got that predictor variable, you'll notice that there's only a dichotomy. So you can really only have either two groups or two measurement occasions. When we have a categorical independent variable that has two or more levels, we can do a one-way ANOVA. And then when we have two categorical variables, we can do a factorial ANOVA. But you'll notice that all of these outcomes are continuous. So what about when we have a dependent variable where the dependent variable is also categorical? That is, the values can only take on um, the values of that outcome variable have to be distinct categories. So we're going to learn two tests for this. So we've got really just we can say a single categorical variable. We're going to use a chi-square test for goodness of fit. And then when we've got two categorical independent variables, we're going to use a chi-square test for independence. So the chi-square test for goodness of fit is a hypothesis testing procedure that examines how well an observed frequency distribution fits with the expected distribution. So what we're doing is testing how well our data fit our expectations under the null hypothesis, which is a general theme for all of statistics, really. Here we only have one categorical variable, so the table might have been a little bit confusing. We just have a single categorical variable. Okay, the levels can just take on these different categories, and we're going to say, is the frequency of observations that we have at each level of this variable, does it match what we would expect if the null hypothesis is true? So much like a t-test for a single sample or a one sample t-test, this is fairly rare in real research settings, but every now and then you will encounter it in professional practice, so it's worth learning. It also sets the basis for learning about the chi-square test for independence. This is a hypothesis testing procedure that examines whether the distribution of frequencies over the categories of one nominal, aka categorical variable, are unrelated to, in other words, independent from, the distribution of frequencies over the categories of another nominal or categorical variable. Okay? We can say that more simply as this is a statistic that tests to see whether there is a relationship between two categorical variables. Okay, that's the simpler. This is this is the more precise way of saying it, but the simpler way to say it is this is a hypothesis testing procedure that will let us know whether or not there is a relationship between two variables. So we do this when we have two categorical variables and we're testing whether the variables are related or if the null hypothesis of independence is a better fit. Okay, the word independence is another way for saying that things are unrelated. Okay, so here's our chi-square test for goodness of fit, and I'm going to use some very simple examples to illustrate these techniques. Okay, so with a chi-square test for goodness of fit, the key idea is the comparison of observed and expected frequencies in each category, okay, or we could say each level of the categorical variable. So an observed frequency is the number of people that are actually found in the study to be in a category or a cell. I'll be using the word cell to refer to the kind of the boxes in the table. So I'm going to show you several tables, and in these tables, a box in the table is a cell. So that's an important bit of vocabulary. The expected frequency is the number of people in the category expected if the null hypothesis is true. Or were true, but is true. Okay, so here's our simple example. Do people show a preference for Coke versus Pepsi? So back in the 80s in particular, it was even in the 90s, Pepsi would go out and do this Pepsi challenge. Okay, would go out to grocery stores and malls and things like that and do blind taste tests. Okay, give people Pepsi, give people Coke, unmarked cups, have people taste it, say which one tastes better, what do you like, and according to their research, more people preferred Pepsi than Coke in these blind taste tests, and this became known as the Pepsi challenge. So let's just say that we're going to do that, okay? And we're going to give 50 people a blind taste test to see which cola they prefer. Under the null hypothesis, an equal number of people would prefer each cola. Okay, so if there is no preference, remember that our null hypothesis is always starting with a no effect or a null. So if there's no effect of one cola versus the other, we expect, well, there's no preference, and roughly equal numbers of people should prefer one to the other. Okay, so with that in mind, if we give 50 people a blind taste test, we expect that 20 people are going to say that they like Pepsi and 20 are going to say that they like Coke. However, our alternative hypothesis is that there is a difference in the number of people who prefer one cola over the other. And in this simple example, we would be expecting that more people would prefer Pepsi, of course, if we work for Pepsi. But we're just going to say the alternative hypothesis is just that there's a preference in one direction over the other. Okay. Yes, so right, that's what I said. So if we work for Pepsi, we're likely to predict more people prefer Pepsi to Coke. Okay, so what we're going to do is test whether what we actually observe, right? So that you actually give 50 people the taste test and say one or the other. You have to choose either Coke or you have to, well, they don't know which one. You have to choose this one or this one. The one on the left, the one on the right. Okay, and then we record, did they actually choose Pepsi or did they actually choose Coke? And it has to be one or the other, can't be both. Okay, and is what we observe different than what we would expect by chance under the null hypothesis, focusing on the frequency of people in each group that chose one versus the other? So the observed frequency is the number of people actually found in each cell of the research design. So in the table, only two options, Coke or Pepsi. How many people actually chose Coke? How many people actually chose Pepsi? The expected frequency is just the number of people expected in each cell if the null hypothesis is true. Okay, and again, we kind of have in our mind, in this little study that we're doing, there's 50 people. So if there's no preference for one versus the other, we're expecting 25 and 25. Okay. So the logic of chi-square is this. if the null hypothesis is true, what we actually observe should match what we expect, okay? So there should be zero difference between what we observe and what we expect under the null. Okay, so if the null is true, we should actually get 25 people picking Coke and 25 people picking Pepsi, in which case there's zero difference between what we observe and what we expect under the null hypothesis. However, if the alternative hypothesis is true, what we observe, the difference, we can say the difference between what we observe and expect would be something that is different than zero. Okay? So in other words, if people do prefer Pepsi, we're going to expect more than 25 people to pick Pepsi, in which case what we get in that cell of the design is a difference that is greater than zero, looking at the difference between what we observe and what we expect. So here's our chi-square statistic. What this chi-square says to do is we're going to look at the difference between what we observed versus what we expect. We're going to square that difference. We're going to divide by what we expected in the first place, and then we're going to take the sum of what we expect minus what we observe minus what we expect squared over what we expect for each cell of the design and sum that up. It's similar to calculating variance. We end up squaring each difference so they don't cancel out. Very common theme throughout the class is that if we just look at deviations from the mean and sum them up, they sum to zero. If we look at our regression errors that are either over predicting or under predicting, and we just sum those up, those will cancel to zero. Same thing here. If we look at the difference between what we observe and what we expect over all the cells in our design, if we're to sum those up, they'll also sum to zero. So we have to do this very common thing in statistics where we end up squaring our differences so they don't sum to zero or cancel out. Then what we're going to do, what the formula does, is it divides the squared difference by the difference that we expected, okay, or by the expected frequency. And this is just to give a particular amount of weight to each cell in the design. So in the example that we're talking about, the expected frequency in both cells of the design, so Coke and Pepsi is 25, it's the same, they're given the same amount of weight. But there are other research situations or applications where the expected frequencies in each cells are not exactly the same. Okay? Here would be an example. Let's just say that we've got a population in which the percentage of men and women is different. So, for instance, there are typically more female students that decide to major in psychology than male students. And so sometimes that can be like 60% or 70% of the psychology majors are women. A certain instructor might want to know if the demographics in his or her classroom are similar to the overall demographics in the major. And so what that instructor might be asking is to say, okay, I'll just keep the numbers easy. I've got 100 students in my class. If I know that 60% of psychology majors are women and 40% are men, I expect to find 60 women in my class and 40 men in my class. So that's an example in which the expected frequencies are in those two cells are not equal, but they are based on a null hypothesis. Okay, and then so the instructor can test: do my observed frequencies depart from that number? Like, am I somehow attracting more women, or am I somehow attracting more men? Okay, they can test that hypothesis. And in doing the statistic, knowing that you start out expecting 60 versus 40 will be captured in that expected number. All right, a little bit of a sidebar, but and then ultimately we sum the observed minus expected squared over expected. to account for the totality of differences in those different cells in the design. All right. So therefore, the chi-square statistic is the sum of the weighted square differences between what we observed and expect. All right. So in our example, what's our expectation under the null hypothesis? Okay, so if the null hypothesis is no preference with 50 participants, we're going to expect 25 to select Coke and 25 to prefer Pepsi. That is our expectation under the null hypothesis. Okay, I'll leave it at that. So if the null hypothesis is true and the preference for Coke and Pepsi is exactly equal, what would chi-squared equal? Okay, so I think it's illustrative of how the statistic works to take this example. So if the null hypothesis is perfectly true and we actually observe 25 people that like Coke and 25 people that like Pepsi, which is exactly equal to what we expect under the null hypothesis, what is that chi-square value going to be? Okay, well, the way that the chi-square works is what we do first is we look at this cell in the design and we say we've got 25 people that we observed, 25 people that we expected. Okay, we're going to take the difference between 25 and 25, which is 0. We're going to square that and then divide by what we expect. We'll do the same thing with Pepsi. Okay, we've got observed minus expected squared over expected. So what you can see is that we end up with 0 over 25 plus 0 over 25, which is 0. Okay, so we will always get a chi-square statistic of 0 when our observed frequencies are exactly equal to what we expect. So under the null hypothesis, when the null hypothesis is exactly true, we will get a chi-square of 0. What if we observe that people have a preference? Okay, so here's an example of some data which indicate that people prefer Pepsi. 35 people selected Pepsi, only 15 people selected Coke. How will that influence the size of our chi-square? Okay, so we calculate the chi-square in the same way, and we're going to do it for both cells in our design, so for each levels of our categorical variable. So for Coke, we look at the difference between what we observed versus what we expected. Okay, observed, expected, and we're going to square that number. So hopefully we can just do that math in our head, and we see that the difference between 15 and 25 is negative 10, and when we square negative 10, we'll get 100. Okay, so we've got 100 over 25. What about this next cell in the design? We've got Pepsi, so we've got 35 minus 25 is 10. Square that as 100 divided by 25. Okay, so that's the way that chi-square statistic works. Notice that we don't take the sum until we've done this entire operation. Okay, that's why we see the plus here. This is how we're summing, is we're doing the entire this entire operation. We're doing observed minus expected squared over expected, and we're doing that for each level of our categorical variable, okay, and then we're summing those up. So very important, we've seen formulas before where the summation was actually in the numerator, okay. Here, very important to call out that the summation sign is for this entire quantity. So it's an order of operations that we need to pay attention to. And again, hopefully you see the importance of doing the squaring procedure. If we just looked at the differences between observed minus expected for both cells in the design, and if we didn't square, we get a negative 10 here and a positive 10 here, so we see that those will perfectly cancel out. All right, so 100 over 25 plus 100 over 25 is 4 plus 4 equals 8. So in this situation, our chi-square is equal to 8. But as we know in statistics, we need to evaluate the chi-square that we have obtained against a critical value. Because even though we expect our expected chi-square under the null hypothesis is 0, that doesn't necessarily mean that we're always going to get a chi-square of 0. Just because of random chance, just because of sampling error, we could get a chi-square that is larger than 0, but still not be statistically significant. That is, we could observe differences between our observed frequencies and our expected frequencies, and those differences could simply be due to chance. For instance, what if we had, let's go back to this example, what if we had 26 people prefer Pepsi and 24 people prefer Coke? We would get a chi-square that is not 0, okay? But we would say, but that doesn't look like there's much of a preference there. So even though our chi-square is not 0, that would not be sufficient evidence to rule out the null hypothesis. Okay. What if we got 27 people preferring Pepsi and 23 people preferring Coke? Again, the chi-square is not going to be 0, and that chi-square value is going to get larger and larger. What if we've got 28 people preferring Pepsi and 22 people preferring Coke? Is that a big enough difference? So what we do with our critical value is say, what is a chi-square that is just too big, okay? That we get a chi-square that is too big that we have to rule out the null hypothesis, that we need to reject the null hypothesis because a chi-square value that big, based on differences in observed versus expected frequencies, simply could not happen, simply wouldn't happen due to chance if the null hypothesis was true. Okay. So what we need to do is say, how big can that chi-square statistic get before we're going to reject the null? And much like statistics that we've learned so far in this course, there is a sampling distribution for the chi-squared statistic, and this is a chi-square distribution. This is a mathematically defined curve that we're going to use as a comparison distribution. Just like a T and an F distribution, the shape of the sampling distribution will depend on degrees of freedom. And I'll tell you how to calculate degrees of freedom. Well, degrees of freedom for a chi-square test of goodness of fit is just the number of categories minus 1. Simple. Number of categories minus 1. So in our example, we just had 2 categories, Coke or Pepsi, so we have n minus 1 degrees of freedom is 1. Okay, so this is what our sampling distribution of the chi-square looks like. So you can see the most common value that we would expect is 0, but we would expect that a 1 could happen, a 2 could happen. You know, we can get small values of chi-square that are non-zero, and that can happen, let's just say 95% of the time if the null is true. However, what we're going to do is select this cutoff where we're going to say, hey, we're interested in chi-squares that happen less than 5% of the time if the null is true, and that will be our basis for saying, oh, that's a big chi-square, so those observed frequencies really depart from the expected frequencies under the null, and therefore we reject the null, and there must be, in this case, a preference between Coke and Pepsi. So chi-square distributions are positively skewed because a chi-square statistic can never be lower than 0. That's the same with an F value, by the way, is that because it is a squared statistic, it can never be 0, but it can be much higher. Our chi-square table is going to give us cutoff scores on the chi-square distribution for various degrees of freedom as well as significance levels. So degrees of freedom is just a number of categories minus 1. As I said previously, because we have 2 categories, our degrees of freedom is 1. At a desired alpha level of 0.05, corresponding to sample results that happen less than 5% of the time, if we assume that the null is true, our critical value would be 3.84. Okay? So what that means is that if we calculate a chi-square that is something less than 3.84, we will have insufficient evidence to reject the null. However, if we find that our observed frequencies differ from our expected frequencies, so much so that they produce a chi-square that is greater than 3.84, then we'll reject the null hypothesis and say, hey, there must be a preference between Coke and Pepsi. Okay? And indeed, we calculated a chi-square that was 8. So that chi-square is larger than our critical value of 3.84. It falls in the critical region. So our conclusion is that we're going to reject the null hypothesis. People do not have the same preference or equal preference for Coke and Pepsi. People prefer Pepsi. So we can be specific, okay? The alternative hypothesis was just that there will be a preference for one Coca-Cola over the other, but we can look at the numbers. 35 people said Pepsi, only 15 said Coke, so we can say, based on these data, it seems to be the case that people in general have a preference for Pepsi. Certainly among the sample data, but it would rule out in a more general way that there's an equal preference. And this is what this would look like if you would read these results, say in a research report. People might write up that more people prefer Pepsi to Coke. And it's very common to give the percentages. Okay, so rather than saying 35 people versus 15 people, or even 35 out of 50, it's worth saying it's just simply more descriptive to give the percentage of people that prefer Pepsi to Coke. So 35 out of 50 is 70%, and 15 out of 50 is 30%. So you can say people prefer Pepsi to Coke, 70% to 30%. The chi-square that was calculated with 1 degree of freedom based on 50 people was 8. And we did find that that was statistically significant using an alpha of 0.05. So we just say that the probability of getting this chi-square is less than 0.05. Okay. So if the null is true, there's a less than 5% chance of getting a chi-square that big. That's the literal interpretation. If the null hypothesis is true, there is a less than 5% chance of getting a chi-square that big. Here's another example. Do students differ? This is a silly example, but we just use simple examples to illustrate this statistic. Do students differ in their favorite style of music? Okay, so 51 students were asked. Here are the results. So we've got the observed number of students that prefer each one of these 5 genres. Okay, so we can extend this beyond just two categories. Okay, you can have as many categories as you want. So here we've got 5 different categories. Okay, so let's put on our thinking cap. How do we determine the expected frequency? Well, under the null hypothesis, there would be no preference. Okay, the null hypothesis would say students do not differ in their favorite style of music. And so if students do not differ in their favorite style of music, we'd say that there's roughly equal numbers that prefer each style. Well, given 1, 2, 3, 4, 5 categories and 51 people, what would an equal preference or an equal number of people be in each one of these categories? It's just 51 divided by 5. I suppose I could have used a round number like 50. 50 divided by 10, 50 divided by 5 would be 10, but just wanted to illustrate something, which is that it's perfectly acceptable to have decimals in terms of our expected frequencies. Completely fine, completely appropriate. You don't need whole numbers. Okay, so you can see that we've got the 50 people, and then to divide that 1, we've got a 0.2 in each category. So the expected frequency in each category under a null hypothesis where there is equal preference would be 10.1 in each category. And then we calculate the chi-square statistic in the exact same way, but the calculation is just a little bit more work intensive, because we have to, for each one of our categories, we have to do observed minus the expected squared divided by expected. Okay, we have to do that for each one. So here we go. We're just going to take observed minus expected squared divided by expected. And we're going to do that for each category. And when we do that for each category, we'll then sum up the result. So there we go, and there we go. Okay, so there's all the work. Now what you see on this bottom line is each category's contribution to the chi-square. Okay, so the total chi-square is 12.8. And that total chi-square we got by summing up 3.3, 3.3, 0.141, and 5.08. It can be illustrative to look at each cell's contribution to the chi-square is a way to say where, in what categories does the observed depart or differ from the expected. And a bigger number means more of a departure from what was expected. So here we can see that the biggest number that is contributing to chi-square is this 5.08. And that kind of makes sense because we see the biggest difference between observed minus expected. Here, if we look at the middle category, the number of people that said that they preferred hip hop versus what we expected, we see a very small number. So this is a small contribution to chi-square, only 0.14, because there's not much of a difference at all between what we observed and what we expected. So it can be informative to look at each cell's contribution to the chi-square. Okay, here, in order to come up with our critical value, we have to determine degrees of freedom. Degrees of freedom are 4 in this case because we had 5 different levels of that categorical variable, or 5 different categories. So at a desired alpha of 0.05, our critical value is 9.488. 9.488. Oh yes, there we are. Okay. Because our obtained chi-square of 12.82 is greater than the critical value, we're going to reject the null hypothesis. So what we can say is that students do not have the same preference for music. Now, you'll notice that this kind of takes the same form as conclusions that we had when we were doing our analysis of variance. When we did an analysis of variance, recall that the F ratio is an omnibus test. It just says whether there's a overall differences between cell means. Here we've got a similar type of a situation where our chi-square is this omnibus test. It just says that overall we can say that students do not have the same preference for music. Okay, there's differences between what we observed and what we expected. But we need to do follow-up tests in order to pinpoint in which categories do we see that we're getting more versus less students preferring one type than what we expected. Okay, so just like this one-way ANOVA, chi-square is an omnibus test. And so we need to test to see what the differences in any of the specific cells. So follow-up tests are necessary to determine which cells are different from one another. Okay. Follow-up tests can be performed using the chi-square statistic again and just correcting for experiment-wise error. So this is very similar to what we did with our follow-up tests, following up ANOVA and correcting for experiment-wise error using a bond-friendly correction. Okay. So for instance, we might want to know, are rock and pop different than all of the others? Okay, so do more students prefer pop and rock versus the other 3 categories? So we could say combined, do more people like pop and rock than hip hop? That'd be 1. Pop and rock combined versus country. Pop and rock combined versus electronic. So there's 3 comparisons there. These are just examples, by the way. Okay. Another example we could ask is we could say, is hip hop different from country? And is hip hop different than electric? That would be electronic. That would be 2 comparisons. Or we could just do, is country different than hip hop? Okay, just examples. So if we wanted to test all of those, there would be 6 total comparisons. So recall that a Bonferroni procedure adjusts our alpha level for each test. So if we wanted to do these 6 different comparisons, we would take our overall alpha level of 0.05, divide by the number of test 6, and we would need to get determine a critical value for the chi-square statistic that would be, we could say, significant at 0.001. If we only did 5 tests, we could use an alpha of 0.01. That's what we'll do here, okay? We use a desired alpha of 0.008. Let's just round up to alpha of 0.01, okay? And then to do each of these single comparisons, we're just going to compare one category versus another, okay? So it's these 2 category comparisons, so there's only 1 degree of freedom, okay? So with that, with 1 degree of freedom and we're using a corrected alpha here of 0.01. We adjust our critical value, okay? And again, this is a correction to make sure that we don't accumulate this experimental-wise error. So we're going to make things tougher on ourselves when we're doing these comparisons, a higher critical value. So we need now a critical value of 6.635. So this would be an example of one pairwise comparison where we're just going to take pop and hip hop. Okay, so going back to the original cell in the design, we're going to say, do more people prefer pop versus hip hop? Now there's one important adjustment, okay, which is that we need to adjust our expected frequencies. So if we've got 16 people that said that they prefer or they like to listen to pop, and 9 that said that they like to listen to hip hop, you'll notice that that's 25 people. So what we're going to do is we're going to go back to that null hypothesis of equal preference, and we're going to use our new number, okay, of 25 people, and we're going to split that 25 equally into 12.5 and 12.5 across both of our categories. And then once we've done that, we just calculate our chi-square statistic in the same way. Okay? Following through with the calculations, we get a chi-square of 1.96, which does not exceed that critical value of 6.63 that we previously established. So what we can say is that the differences that we have observed between what we observed and what we expected is not large enough to reject the null hypothesis. Okay, so we would fail to reject the null hypothesis that there's an equal preference. So essentially we're saying these are insufficient data to conclude that there is not an equal preference between the two. We have to accept for the time being that there is an equal preference among students between these 2 categories of music. What about pop and electronic? Notice here that, again, we've had to adjust the expected frequencies just by taking the observed number, the total observed number of 19, 16 plus 3 is 19, and then splitting into 2 for equal preference. Following through the chi-square the same way, we get a chi-square of 8.9, which does exceed the critical value of 6.63. So these frequencies are significantly different, and we can say that more people prefer pop, less prefer electronic than expected under the null hypothesis. Okay, we expected 9.5 and 9.5, so we can say more people preferred pop than expected and fewer people preferred electronic than expected.